Have you ever wondered how a massive metal bird, weighing hundreds of tons, can soar effortlessly through the sky? It's not magic, it's science. The science of aerodynamics. Welcome to our deep dive into the invisible forces that make flight possible. Aerodynamics is the study of how a moves and how it interacts with objects moving through it, like an airplane, a race car, or even a simple kite. It's the art of riding the wind, and today, we are going to unlock its secrets. To understand how anything flies, we need to master the four fundamental forces that are always at play. Think of it as a constant tug-of-war in the sky. These forces are lift, weight, thrust, and drag. Let's break them down one by one. First up is the hero of our story, lift. This is the upward force that opposes gravity and keeps the plane in the air. But how is it generated? It all comes down to the special shape of an airplane's wing, known as an airfoil. An airfoil is curved on top and flatter on the bottom. As the plane moves forward, the air splits to flow over and under the wing. Because of the curved upper surface, the air traveling over the top has a longer path to cover and must move faster than the air moving underneath. This is where a key concept in physics comes into play, Bernoulli's principle. In the late 18th century, a Swiss mathematician named Daniel Bernoulli discovered that as the speed of a fluid, like air, increases, its pressure decreases. So, the faster moving air above the wing creates a zone of lower pressure, while the slower moving air below the wing maintains a higher pressure. This pressure difference creates a net upward force, pushing the wing, and the entire aircraft, upwards. It's like the plane is being sucked into the sky. The amount of lift generated depends on the wing shape, its size, the speed of the aircraft, and the angle at which it meets the air, which we call the angle of attack. Pilots can control lift by adjusting these factors, allowing them to climb, descend, or maintain a level altitude. Next, we have weight. This one is pretty straightforward. Weight is the force of gravity pulling the aircraft down towards the center of the Earth. Everything has mass, and gravity acts on that mass. For an aircraft to get off the ground and stay in the air, the force of lift must be greater than the force of its weight. Once it's cruising at a constant altitude, lift and weight are perfectly balanced. The challenge for aircraft designers is to build planes that are incredibly strong and durable, yet as lightweight as possible. That's why modern aircraft are built from advanced materials like aluminum alloys and carbon fiber composites. Now, an airplane sitting on the runway isn't going to generate any lift. It needs to move forward, and that's where our third force comes in, thrust. Thrust is the forward-pushing force that propels the aircraft through the air. It's generated by the engines. In propeller planes, the engine spins blades that are shaped like small wings. These blades grab the air and push it backward, which, according to Newton's third law of motion, creates an equal and opposite reaction that pushes the plane forward. For every action, there is an equal and opposite reaction. Jet engines work on a similar principle but in a more powerful way. They suck in a huge amount of air at the front, compress it, mix it with fuel, and ignite it. This creates a high-pressure, high-temperature gas that blasts out of the back of the engine at incredible speed. This powerful exhaust stream propels the jet forward with immense force. Thrust is what overcomes the forces of resistance and gives the plane the speed it needs for the wings to generate lift. And that brings us to our final force, drag. Drag is the aerodynamic force that opposes an aircraft's motion through the air. You can feel drag yourself by sticking your hand out of a moving car window. It's a form of friction, or air resistance. Drag wants to slow everything down. There are two main types of drag. The first is parasite drag, which includes things like skin friction, the air rubbing against the skin of the aircraft, and form drag, which is caused by the overall shape of the object. A boxy shape will have much more form drag than a sleek, pointed one. The second type is induced drag. This is the drag that is an unavoidable byproduct of generating lift. The high-pressure air under the wing tries to spill over to the low-pressure area on top, creating swirling vortices at the wingtips. These vortices disrupt the airflow and create a backward pull on the wing. Engineers and designers are constantly working to minimize drag. This is why airplanes are so beautifully streamlined, with smooth surfaces, pointed noses, and tapered tails. Even the rivets used to hold the skin together often flush with the surface to reduce drag. The winglets you see on the tips of many modern airliners are specifically designed to reduce those wingtip vortices, which cuts down on induced drag and improves fuel efficiency. So, in flight, these four forces are in a delicate, constant dance. For an aircraft to take off, thrust must be greater than drag, and lift must be greater than weight. To fly at a constant speed and altitude, thrust and drag are balanced, and lift and weight are balanced. To slow down or descend, the pilot reduces thrust, and drag becomes the dominant force, or they adjust the wings to decrease lift. The journey to mastering these forces is a story of human ingenuity and courage. Long before the science was fully understood, pioneers dreamed of flying. In the late 19th century, a German engineer named Otto Lilienthal became known as the Glider King. He made over 2,000 successful flights in gliders he designed, meticulously studying how to control his flight by shifting his body weight. His work was revolutionary, but it also highlighted the dangers. He tragically died in a glider crash, but his last words were reportedly, "Sacrifices must be made." His research directly inspired two bicycle mechanics from Dayton, Ohio, Orville and Wilbur Wright. The Wright brothers were different because they realized the key to successful flight wasn't just about getting into the air, but about controlling the aircraft once it was there. They systematically studied aerodynamics, built their own wind tunnel to test wing shapes, and developed a revolutionary three-axis control system that allowed them to steer their aircraft. On December 17, 1903, at Kitty Hawk, North Carolina, they achieved the first successful, sustained, and controlled powered flight. That moment changed the world forever. Since the Wright Flyer, aircraft design has evolved at an astonishing pace. Early biplanes with their struts and wires created a lot of drag. As our understanding of aerodynamics grew, designs became more streamlined. We saw the advent of the monocoque fuselage, where the skin of the aircraft bears the structural load, allowing for smoother, more aerodynamic shapes. Engines became more powerful, and planes flew higher and faster, leading to new challenges like supersonic flight and the sound barrier. The quest to cheat the wind and reduce drag has shaped every aircraft you see today. But aerodynamics isn't just for airplanes. The principles are everywhere. Look at high-performance race cars. They use inverted wings, or spoilers, to generate downforce. This is literally negative lift. It pushes the car onto the track, increasing the grip of the tires and allowing it to take corners at breathtaking speeds. Aerodynamic shaping on cars also reduces drag, which is a major factor in improving fuel efficiency for the cars we drive every day. Even rockets, which spend most of their journey in the vacuum of space, rely heavily on aerodynamics during their launch and re-entry phases. They need to be stable as they punch through the densest part of the atmosphere, and spacecraft like the Space Shuttle had to be designed as gliders to safely navigate their way back to a runway on Earth. And of course, nature is the original master of aerodynamics. Birds are living marvels of aerodynamic design. Their bones are hollow to save weight. Their feathers can be adjusted to change the shape of their wings, allowing them to soar, dive, and maneuver with incredible agility. The shape of a peregrine falcon's body, for example, is perfectly streamlined to allow it to reach speeds of over 200 miles per hour in a dive. By studying birds, and even insects, scientists and engineers continue to find inspiration for new and more efficient flying technologies, a field known as biomimicry. So, the next time you look up and see an airplane gliding across the sky, remember the invisible forces at work. It's a beautiful symphony of science, a perfect balance of lift, weight, thrust, and drag. From the early dreams of flight to the sleek, efficient jets of today, our journey into the sky is a testament to our understanding and mastery of aerodynamics. It is the science that allows us to slip the surly bonds of Earth and dance on the wind. Thanks for joining us on this journey through the fundamentals of flight. If you enjoyed this explanation and want to learn more about the amazing world of science and engineering, be sure to like this video and subscribe to our channel. Fly high, and we'll see you in the next one.